Welcome, welcome to lesson 24. Everything just kind of like this river is all running to one particular place by this rhododendron and wedged between these rocks. Likewise, the course is leading to where we are now. We need to complete a lesson 24, which is facts about the chi-square distribution. That's not chi-square, it's chi-square distribution, chi-square distribution, I should say. And that's a Greek letter chi. And this is a really short lesson. This just introduces and gives some facts to you guys. And when I laid out the class, I did it based on people who have taught the class before me, and they dedicated a whole lesson to this. So I did in my planning, but it's going to be a pretty quick lesson. And what we're going to do is a worksheet that will review a lot of the things we've done during the course of the year, because at the same exact time that we're starting to work toward these last two lessons, we're also starting to segue toward your third test of the year, which all our tests are cumulative, and also your final exam. So let's get started. Our agenda for today: first, the chi-square distribution; second, some general review material, and also some specific review material for the test coming up. Those two things will be contained on the worksheets. The way we're going to do the worksheet is we're going to do this brief video lesson now about the chi-square distribution, and then I'm going to give you, it's already on Moodle, the worksheet for today. You'll answer those questions, and then I will give video answers to those questions, several different videos that go over the questions in detail. All right, so introducing the chi-square distribution. The chi-square distribution is actually a family of distributions, and each distribution is defined by the degrees of freedom. Now, it's very difficult to explain the degrees of freedom, and I don't think I'm 100% capable of it, but I can work with it, okay? And I think that you'll see that most of the work we do with this is pretty formulaic, so I don't think it will be difficult for you. All right, degrees of freedom are discussed in greater detail on different pages in the book, and we will get to it a little bit, but mostly we're going to say the degrees of freedom are, or you will calculate them in an easy way. The figure below shows three different chi-square distributions with different degrees of freedom. Okay, and basically your degrees of freedom are related to the sample size. So if your degrees of freedom, that's df in the graph, is really minimal, like the purple graph, if it's 3, well, that would be a positively skewed graph, big time skewed. If it's 4, it's a little less skewed. Okay, well, what if we bring it up to 8? Well, now we're getting something that looks more and more like a normal curve. So as the sample size increases, basically the degrees of freedom will also increase. Maybe not 1 for 1, but pretty similar to it. So whereas the sample size might be 100, the degrees of freedom might be 99, 98, 97, but it'll be up there. And the higher the degrees of freedom go, then the more and more the shape looks like a normal curve. Just like the blue graph looks more like a normal curve because its degrees of freedom is 8 than the purple graph, which is 3. So the big thing that you need to realize now is that the greater the degree of freedom, the more the graph looks like a normal curve. The higher the degrees of freedom for a chi-square distribution, the more it looks like a normal distribution. Now, from your textbook, the notation for a chi-square distribution is, and the thing that chi-squares are all about is the squaring of chi. And by the way, chi is a Greek letter, and it looks like an X, but it's not exactly an X. And if you look closely, you'll see the difference. One of the lines making up the chi symbol is a straight line. The other one's a little curved. All right, so it's going to be the chi squared and the degrees of freedom that make it up. So the degrees of freedom, which depends on how the chi-square is being used. For our purposes, for now, we'll use the degree of freedom as n minus 1, where n is going to be the sample size, how many samples we're going through. So the degrees of freedom for the 3 major uses for each are calculated differently. So for now, we'll just go with n minus 1. We are not, absolutely not going to go crazy on this. for the chi-square distribution, okay, the population mean is the degrees of freedom, and the standard deviation is the square root of 2 times the degrees of freedom, which is 2 times mu, or the mean. The random variable is shown as chi-squared, but it can take any upper class letter, okay? Now, basically, this is it. The random variable for a chi-square distribution with k degrees of freedom. So notice, there's k degrees of freedom, and there's k of these different normal variables, okay? So that's the big thing, is that the degrees of freedom will equal the number of independent normal variables, okay? The curve is non-symmetrical and skewed to the right if it's 1. See, here's the degree of freedom of 2. Look at how that curve looks. Now look at the degree of freedom of 24. The more the degree of freedom is, the higher the degree of freedom number is, the more and more it looks like a normal curve, okay? But for every single degree of freedom, there's a slightly different looking chi-square curve. Say that 10 times quick. All right. And the last thing we need to know for the chi-square is that the test statistic for any test is always greater than or equal to 0. Yeah, can't have negatives. And when the degree of freedom is greater than 90, the chi-square curve approximates the normal distribution. All right. So for this notation means the chi-squared of 1,000 degrees of freedom, the mean is 1,000, and the standard deviation is 2 times 1,000 square root of, which is 44.7. Therefore, the normal curve, see, here we go. Now we're showing how, as we're getting up in big numbers greater than 90, how we look like a normal curve. The normal curve with a mean of 1,000, standard deviation of 44.7. Right? So in other words, in case you haven't noticed, pretty much everything, including the chi-square curve and distribution, always comes back to a normal curve. So if your understanding of a normal curve is strong, and I believe it's very strong, that means that you will understand this well. Okay? Next, the mean is located just to the right of the peak, and that's because the tail goes a little bit to the peak. So the mean pulls the tail up just a little bit. But it's almost a normal curve, so that allows us to do some, or implement some normal curve ideas. So I think the purpose of this lesson was just to get everything set up so that you've seen a few chi-square distribution terms. We want to get to the idea that a chi-square distribution, as we get higher than 90, the degrees of freedom higher than 90, then it begins to really take on the shape of a normal curve, and that's where we can introduce normal curve notation. Also remember, to find the standard deviation, it's the square root of 2 times the degrees of freedom. All right, so that's really the major points that we're looking to hit here. Also, don't forget, the greater the degrees of freedom, the more and more the curve looks like a normal curve, the chi-square distribution curve. All right, so that covers, believe it or not, this is the topic that the other professors had. And had I known back in the day that the topic was this brief, I may have done things a little bit differently. But with only 2 lessons left, I prefer to do this for a day, catch our breath, do some review, and then next class we'll move forward to some applications of the chi-square distribution. All right, so I'm going to stop recording this now, and the other thing you need to do at this point is start working on the worksheet. Complete the worksheet and then watch the videos for the rest of the lesson. And when you're done watching those videos, then I'll feel like we're progressing toward the kinds of questions that you can expect to see on your test in a few more days. Have a good one. Bye-bye.